Hello, my name is Rasmus Bro from Chromath. I just wanted to talk a little bit about limit of detection. Um, I have a data set here. You can see, if you can read here, it's about 10 years old. Some fermentations we were measuring GCMS on, and at that time, the data was integrated with ChemStation, yielding 21 different metabolites of flavor compounds. And I want to take a look at one of them, acetone. You can see that there's a number of zeros here. Let me actually show you a plot of this. Here you can see this is basically following a fermentation with one species, another species, and another species. So we have kind of three different fermentations, actually two fermentations of each. Anyways, what you can see is that when we get below a certain value, a certain threshold, you're not able to detect the peak, and you need to be able to see the peak in the individual sample in order to quantify it. And so there's a lot of samples here where we basically just say below limit of detection. And in this particular case, they are then set to zero. There are different strategies for what you can do. And I just want to show you that we don't have limit of detection in Paradise. And let me show you how that works. Here's the actual GC data or the ticks. And the acetone is in around 18 minutes. So let me see if we can zoom in a little bit. It's around this area here. Let's see now. So it's this peak here. So let me actually go. I already did the analysis and I can't remember exactly how many components. It's not really critical. Any number around here is going to give you more or less the same. So let's see now. Well, you can see that this is a 7-component model. Let me turn on the viewing of all the different 7 components. So some components are describing the shoulder here. There's another peak here. That's why the automatic peak detector has found 2 peaks over here. And then there's a lot of baseline as well. But let me turn these off. So yeah, here we are. So we have this light green one. That's the one we're interested in. And we can see the spectra here. So it's the green mass spectrum. If I want, I can look it up in NIST. But that's not super important here. You're going to find that indeed this is resembles acetone quite a bit. But what I want to show you in particular is that when we take a look at the scores, the concentrations, the relative concentrations, and compare them to, let me show you what we had over here. So we kind of had the 2 fermentations with this organism. These ones were basically almost all of them below a limit of detection. And then we had this third one. Now, the sample order is different here. So we have 1 fermentation with this organism and the second one. Then we have 2 of these ones and 2 of these ones. Now you can see not only do we quantify the samples everywhere, but also the quantifications are just nicer. It's a more smooth curve, indicating that the estimates are more accurate and more nice. But look, the samples are quantified in each and every sample. Also, when there's 0, it might be difficult to see, but there are some samples here that have 0 concentration. And Paradise simply doesn't care whether the concentration is 0 or 5 or 100. It'll quantify every chemical in every sample. Now, if you want to call some of this below limit of detection, that's perfectly fine, but Paradise will quantify everything. And when we're doing untargeted analysis, it can actually be quite important to get accurate quantifications in certain cases. There's really no good reason for why you want to set certain numbers to 0 or to below limit of detection in a untargeted sort of multivariate setting. You want all the quantifications. Paradise will quantify perfectly fine whether it's below limit of detection or not. It doesn't affect how well we quantify. I know that some people will not really agree on that, but it really is true, and I'm happy to debate that further. And that's basically what I wanted to show here. Thanks.